this lecture is focusing on concentration and molarity calculations. So the first calculation that we are going to look at, this mass percent concentration, is looking at the mass of my solute over the mass of the whole solution. Referring real quick back to this picture, we are looking at essentially how much solute, so that's our numerator, and we're looking at that in grams, over how much solution. Now, even though this doesn't specifically ask for the solvent, we know that the solute plus the solvent equals the solution. So when I'm looking at that denominator, again, it's in grams, we're able to see this ratio. So I'm going to go back here. So for example, if we have a student that's preparing a solution from 5 grams of sodium chloride dissolved in 119 grams of water. Well, we know that this is my solute, and if it's dissolved in that much water, that's my solvent. So I can get the mass of my solution because we know that solute plus solvent gives me that. So to find the concentration in mass percent, I'm simply going to do 5.00 grams of NaCl divided by my 5.00 grams plus 119 grams, and we're going to multiply that by 100. Now we can reduce down that denominator, so I'm going to have 5.00 grams on top. And remember, while I'm adding, since I am adding, and this is precise to the hundredths, but this is only to the ones, so you go to your least. So I'm going to do 119, so that would be 124 grams. It's not 124.00 because remember, addition sig fig rules, we would go to the ones here and times that by 100, and we should get 4.03%. And if we look to make sure that our sig figs are right, on top we have 3 sig figs, 5.00, and on the bottom we have 3 sig figs. So I need 3 sig figs for my final answer. Now my next problem, it wants to know how many grams of magnesium chloride and how many grams of water. So this is my solute, this is my solvent, my water is my solvent, need to be used to make 455 grams of a 10% mass over mass solution. Essentially what I'm doing is I'm going to have, I don't know how much magnesium chloride, but I know that the total combined is 455 grams of total solution. And we know that we have to times that by 100%. And that equals 10.0%. So now we just have to do some working backwards. First thing I'm going to do is, we know that any time that we're timesing by, like if this was something times 5, this 100, it's the same thing as making that numerator. So what I'm going to do is get rid of this 100. I'm going to divide both sides by 100%. So that cancels. So divide by 100%. So now when I rewrite this, I'm going to have question mark over 455 grams equals 10 divided by 100 would be 0.100, because again, we want to stick with our 3 sig figs. To solve, we need to get rid of this denominator, so we're going to multiply both sides by 455 grams times this by 455 grams. Now that will let us, again, get rid of this. So then I get my question mark, my solute will be equal to 45.5 grams of magnesium chloride. Great. But now we need to figure out, well, how much water was used? I know, and I found that numerator, this 45.5 grams of magnesium chloride. And remember, it told us that this is how much of the whole solution it made, 455. So now all I need to do is subtract the two, because we know that both combined equals 455. And I know that this was the solute that was put into the water. 455 grams minus 45.5 grams should be equal to 409.5 grams. But we do need to make sure that, let's see, when we are following subtraction rules, that we are to the ones here, to the tenths there, so we only can be significant to the ones, which means this 409.5 is going to round up to 410 grams. And then lastly, let's solve this problem. It's kind of similar to this last one. Hopefully, actually, you find it a little bit easier because we don't have to find both pieces. But this one says, how many grams of KOH is in 700 grams of a 5% mass solution? So again, we're going to assume that this grams of KOH is my solute, and it tells me that I have 700 grams. So that's just telling me, making sure that I know that that's 3 sig figs instead of, if it was 700 with no decimal point, that would just be 1 sig fig. So 3 sig figs for this times 100% is equal to 5.00% solution. So again, we're going to divide both sides by 100. So I'm going to have question mark over 700 grams is equal to 5 divided by 100 would be 0.0500. And then I'm going to multiply both sides by, get rid of that denominator, so I need to multiply both sides by 700 point. Multiply by 700 point, and we would get 35.0 grams of potassium hydroxide. And the reason why it's 35.0 is because we got to look at sig figs. So I've got 3 sig figs here and 3 sig figs here. So I need to have 3 sig figs for my final answer. The second way that we're able to calculate concentration of a solution is by finding molarity. Notice that this equation is similar to the other one in the way that it is a ratio. This, though, instead of having grams over grams, is looking at moles of solute over liters of solution. And this is given to us by capital M. That's the representation. So it's not a percent. This is moles per liter. Similar to density, when we do mass divided by volume, it's given to us as, grams per milliliter, or finding the speed of something as how many miles per hour. So this is moles per liter. It tells us the concentration of it. So if I flip back here, similar to our mass over mass percent, where my numerator was in grams, looking at that solute. Now for calculating molarity, we're just going to look at how many moles of solute. And we know how to get from grams to moles. That's our numerator. And then in our denominator, instead of looking at the grams of solution, we're looking at liters of the solution. That's the only difference between it. So we're not looking at grams to grams and then percent. We're just looking at moles per liter. We're going to go back and look at these questions. It wants to know the molarity of a solution made from this many moles of NaOH, so that's my solute, in this many liters of my total solution. Molarity is simply my 0.0600 moles divided by 0.175 liters. We get, and if we look at how many sig figs that we have, I have 1, 2, 3 sig figs on top, and I have 3 sig figs on the bottom. So I need to finish with 3.343, and we simply just need to give it capital M for molarity, because we need to get into the mindset that molarity is moles over liters. Looking at the second one, it wants to know how many moles of potassium bromide. So it wants to know my moles of potassium bromide is in 500 milliliters of this concentration of KBr solution. We need to find, this is my numerator, this is my question mark. Now, remember, molarity is moles per liter. This is milliliters. So we just need to do a quick conversion, going from milliliters to liter. And we know that there's 1,000 milliliters in 1 liter. My liter solution on the bottom would be 0.500 liters of solution. And we know moles divided by liters to get molarity. And molarity here, it tells us 0.1997 molarity of potassium bromide solution. So now we just need to find our missing variable here. And to do that, again, to get rid of this denominator, we're going to multiply both sides by that number, 0.500, over here, 0.500. Again, that's liters, and this should give us our answer. And again, I'm aware that we need to look at sig figs. 500 decimal point is 3 sig figs, and 0.1997 is 4 sig figs. So I can only have 3 in my final answer. So you got to be careful and make sure that because I got 0.09985, so that rounded up to 0.999. All right, let's do one more sample problem. Okay, so the last example from this one. Let's look at how many liters is a 2.54 molar solution, molarity solution, containing 1.7 moles of solute. So again, my solute is always on top. That's my numerator. 1.70 moles over, it says how many liters. I don't know how many liters of that. So remember, moles divided by liter gives me my 2.45 molar solution. So now I just need to rearrange my equation. Okay, so I'm going to show you 2 different ways to do this, depending on how your brain works or how you like canceling out. So I'm going to pretend instead of this question mark, let's make this X. All right, so remember how we did before, to get rid of something, we multiply by it. Well, let's get rid of this X because I just don't like having a variable in the denominator. So if we multiply by X, we're going to get rid of it. But that also means that I have to multiply by X on the right side. So those are going to cancel. So I'm left with 1.70 moles is equal to 2.45 m times X. So that didn't solve the problem for me. If anything, I went from having variable on the left, and now I have my variable on the right still attached to the other number. But now I don't have an ugly fraction. Now to solve for X, right, I just got to get rid of what it's attached to. So I'm going to divide both sides now by 2.45 m. So divide 2.45 m. And that will help me solve for my liters, which should give me 0.694 liters. Now let's do it another way. Remember when I made this nice little circle when we were doing density equals mass divided by volume? And if I covered up density, pretend that's my finger covering up D, it's M over V. Well, we can do a similar setup because essentially saying molarity is equal to moles divided by liters, right? Okay, so if this says how many liters, it wants to know this. So we could rearrange the equation just by looking at this and saying, okay, if I cover up this L, right, if I cross that off, I would say L equals moles divided by capital M, which is molarity. And then I can look at this equation and go, oh, okay, there's my moles. 1.70 moles divided by, there's my molarity, 2.45 m. So either one of those work, you should get the same answer. But looking at the circle, now that I made a mess of it, if I were to write it again here, because we know capital M, molarity is moles over liters. We could rearrange this and I could say, well, we already solved for L. So how would I solve for moles? If I said how many moles of solute would I need? If I covered this up, right? If I cover this up, I would say moles is equal to, these two are next to each other, which means that we would multiply. So it'd be molarity times the volume in liters. Okay, so last, I want to look at this fat simulation again. We did a lot of messing around with it, but what I want you to go back to is coming down here and looking at values. So turn those values on. And let's get something, here we go, potassium chromate. And so what I want you to look at, and remember that molarity right here on the right, molarity is equal to moles of solute over liters of solution. So for example, if I had 0.500 moles of my solute of potassium chromate in exactly 500 milliliters or 0.500 liters. So if I did 0.5 divided by 0.5, you would get 1, right? And that means 1 molarity, 1 moles per liter. And what I would like for you to do is to just kind of mess around and notice how as I increase my amount of solute, which means as I put more potassium chromate in, and I keep the volume the same, notice that my molarity went up, right? It's becoming more concentrated. And so if I did 0.817 divided by 0.5, I would get 1.634 molar. And oh, their sig figs are off. It should only be 3. But I can just do some messing around and say, okay, well, so what if I have, okay, molarity went up. What happens if I decrease my volume? What do you think is going to happen? And oh, if I have moles of solute stay the same, pretty high, but my volume goes down, it's going to become even more concentrated, and we can see that. Versus if I increase the volume, we can see my concentration going down on the right. So why don't you give this a try, do some messing around, try some different compounds here using different solutes, and look and see how that affects the concentration or the molarity of those solutions.